Okay, so even you know how much I love algorithms, data structure, and complexity analysis. And today I thought that we could talk about a really interesting problem that is full with gems about these things, so we can learn a lot from this problem. But first, before we get into this problem, we have to talk about the background. A year and something ago, I approached my professor, to whom I owe great gratitude. This is Professor Dr. Damian Sternat. And I asked him for, can we organize around here at the Faculty of Electrical Engineering and Computer Science in Maribor for newcomers in competitive programming. And to my surprise, he accepted it. So a background a little bit about him. He's the professor that teaches every collection of subjects that I really adore. So this is algorithms and data structures, artificial intelligence, algorithms and techniques for solving problems, advanced algorithms. So this collection of subjects are really my favorite. And he accepted the proposal, so I authored the whole problem set. I drafted around 20 problems, and of which only 5 were picked at the end. So 5 problems, then there was division of 1 problem to bridge the gap, but essentially we ended up with 6 problems at the end for the round. So this was an internal round. It went a little bit unnoticed by the faculty, but it doesn't matter. The students had a lot of fun solving the problems. And the 6th problem is actually this one. So this is called Maribor's New Skyscrapers. So we don't have skyscrapers in Maribor, so it is intended to be like a pun here, like a joke. And it's a pretty simple problem. It is, even though we put it as a 6th problem, the round was created so all of the problems would be solved under 30 minutes, would be solvable under 30 minutes. And we gave them like an hour, 2 hours actually, around 2 hours. Let's have n parcels, so like places where new skyscrapers can be built. And n, I will write here the constraints of the problem. N can go up to 10 to the 9, which means that the amount of places is 1 billion. All of the places have an original height of 0. You are asked to create a program which will answer some questions and which will update the height of each of these places. And these kind of questions, we call them queries. And there are at most 10 to the 5 queries. This is 100,000 queries. All of the queries will be of 2 types. We are just interested of 2 types of queries. One type of query, the first type 1, we will call it build query. This is some kind of, so imagine like you have some database and you want to execute these queries on top of it, right? And this build query will take an integer I and will take a value v and will simply say a of I, so a of I equals v. So I will set the skyscraper which has the ith skyscraper. These are all numbers from 0 to n minus 1. I will simply say that the ith skyscraper will have a value of v, but it is also guaranteed that the ith skyscraper right now is smaller than v. So this is a very interesting constraint that we have. So the v is always going to be bigger than next v. So we will only build up the skyscrapers. We will not have a skyscraper where it will collapse, let's say. And then there's a type 2 query, which these queries can be interchanged. So we can build, then we can ask. And let's say we ask and we get only one integer s. And this is essentially, we ask, what is the maximum value from I equals s to n? So what is the maximum value from s to n of ai? So this is, if I was given 4 and you're asked what is the maximum from this point up till, until the end. For those of you who are already familiar with this kind of problem, you will see that you will immediately think of solving the problem using fanfic tree or segment tree, some complex data structures, right? But I promise you that this will have nothing to do with complex data structures, and you will be able to solve this problem exclusively with one simple data structure that is implemented already in the standard library in no more than, what is this, like 30 lines of code. Shall we do an example?
Of course.
Let's build some skyscrapers first, because if we ask any question right now, the maximum we get is 0, right? Where do you want to build a skyscraper? On which one?
Well, let's go for 5.
Build 5 and some value. What is the height of the skyscraper?
Well, let's go for 100 maybe.
100 meters. That's pretty well. So in 5 we will build a skyscraper that is 100 meters. So I will have here another. Let's say I have here another array. We'll need paper change later, but let's say we have another array. First we will denote all of them with zeros to some endpoint. This is now 100, right? All of them remain 0, so I'm not going to draw. Okay, so we need one. Let's build more, so it's fun.
Well,
okay,
let's build 10.
The 10 value is really far. Let's go up to 7.
To 7.
Just to limit the paper, because we will need hundreds of kilometers of paper.
Okay, let's go for the 7th. And
okay, the 7 and what?
Maybe 155.
150. Let's make a smaller value here.
Oh, okay.
Because it's going to be fun. 80. Okay, so 80. Let's build one more quickly.
Okay, let's go for 2.
Let's go for 2.
65.
65. Excellent. Let's go 1.
Let's go for 3 maybe.
3. Okay.
Wait. Oh, let's go for 110.
110. Okay. Okay, now we have some numbers, right? But now we can ask something. So we can ask, let's ask somewhere. If I ask from 4, right? So ask from 4. This means that I ask for the 4 and up till the end, right? So what is the value here, the maximum value?
For the maximum it is 100.
It is 100. Okay, let's ask one more thing, maybe. Where do you want to ask?
From, I don't know, probably it's okay if we ask from the 3rd.
Okay, from the 3rd. Okay, from here, right? Now here on the 3rd value is already a bigger value, right?
Yeah.
So we will have 110. Again, we can call a build function, and then we can say, okay, let's build on 1 here, let's build, and let's say that this is 200, right? And now we will change this to 200. Or we can actually build upon some other given. So we can, instead of, we can say build 2, right? And we can say that this is 150, then this 2, instead of 65, will change now to 150, right? We will update a bigger height. And so forth, so forth, so forth. So this problem is an interesting problem, right? We want to solve it very quickly, but we don't want to do it, and there's a lot of solutions for this problem. So there can be a solution with segment tree, sparse segment tree, fanfic tree, offline solutions with square root decomposition. So there's a lot of solutions for this problem, right? But the whole idea is to how we can solve it with some simple, intuitive thing, which doesn't require complex data structures, doesn't require anything complex. And this is what I want to talk to you, because this will get us to amortized complexity. Give here a minute for you and the viewers to pause and ponder how we can write these two functions. And then and then we will show you the solution and paper change.
Paper change.
So we're back, and I hope you found the solution.
Actually, I have an idea.
Yes.
Why does it sound like dynamical programming?
That's a really good question. Yes, dynamic programming. It's kind of very close to it. It's very close, and you will see why.
Is it some version of it?
Like
Or-
there is a version of dynamic programming that uses such things. So you could say that it's very close to this. I will show you the solution, but first we will intuitively come to the solution. So we won't go there first. So let's write the array again. Let's put 35 and let's put 100. Doesn't really matter. 0, 80, and so on, zeros until up till the end, let's say. There is n up to 10 to the 9. So even if we want to all of these integers to make it in memory, we can't. There's like gigabytes of memory we need to store each of these integers. But how many at most we will change? Each query be a separate integer, right? A separate skyscraper that will up the value, the height. Then there's at most 10 to the 5 skyscrapers that will change. So we don't need to store them all. We just need to store 10 to the 5, right? But we don't know which ones at first. When we'll get a skyscraper, this is the first time we may get it as a value, right? Okay, so this is one thing we have to deal with. Another thing is, can we somehow make some observation about the answers? What will be the answers in this problem? What can be the answers? So for this array, can you tell me what are the possible answers? So first answer, there could be 0 if I start S from here, right? The next answer could be 80, right? If I start, so there's like 0, there could be 80, the next answer. What if I start from here? Does the answer change?
Well, it doesn't.
Yes, it doesn't.
Yeah.
80 is the maximum value, right?
If we go with 100,
If we go with 100, then
changes.
there's an answer with 100.
Oh,
Here,
if we go with 110 and it doesn't change anymore, right?
so here it doesn't change.
Here it doesn't
change. Here it does change. We have a new value.
I will test. Okay.
So we have a new value here, right? 110. Yes, here we have another value that is bigger, which is 200. You can see that somehow the answer always changes to a bigger value. And in other words, the first observation, what we're gonna write, is very obvious. If we have an I that is smaller than j, the answer, so if I ask at I, will be bigger or equal to that what I ask in j. This is the first observation.
So
right?
we have an increasing sequence, right?
Yes. Yes, exactly. We have something that will always, we want something that will always increase. And here what is very intuitively is why can't we build a data structure that will support this? And this is called, we built a data structure with an invariant. For every I that is smaller than j, we will only keep ai that is bigger than aj. This is our invariant. We won't keep, we know that, for example, 35, because this is 100 here, this here, 35, if I will be here and j would be here, 35 will never change this. It will never change the answer. The answer, for every answer from, starting from this point up to here, for any answer, 100 is the biggest value. 35 will never be the biggest value. We know that because we can never downscale skyscraper. We can only upscale it. We can only increase it in height. So we can just take off these values. Like we don't need these values. We will just remember values that are in decreasing order if this is 0 and that this is n. Because the answer will only change at these points, and these points are sometimes called events. This has a very beautiful geometrical representation, of course, in the sense that if I draw a graph, where this would be an index, and this would be AI, so the value, the height of the skyscraper, right? How much is it? So we had at the index 0, we had 0. Then we had 200, so at index 1 we had 200. So this let's say is here, 200. Then we had an index, then we had 65, which is somewhere here. And zeros in between somewhere, right? So our data, with our data structure, we will say that we don't need these values that are very small because they won't influence the answer. The answer will change only at these points here, the event points. And if I draw a line from this 0, this, you can see that this line is decreasing here in our case, right? We only care about this line. And this line, in some problems, is called a frontier. What happens if I add now a new value? Because this data structure will change, have to change, right? What if I add a value on this index here? What is this like? I don't know, let's say 7, index 7, doesn't matter. Let's say I add the value here, which is somewhere around 65, let's say 60, right? I add this skyscraper 60. Well, will this influence anything, right?
It won't.
It won't, of course. So we don't add it. So this is we don't add it here. But what if I, instead of this value here, which was 35, what if I increase, what if I build upon this skyscraper and I say, well, now it's 180 here.
Now it changes.
Now it changes the frontier. But how does it change? How does the frontier change? This is very important. How does it change? So it changes that we add this value, but this value, does it remain?
No, it doesn't. Now it connects with the 200, right?
Yes, exactly. So the frontier now looks like this. Now this value, we have to delete them. We have to delete this value. So not only that we have to add some values to the data structure and change the frontiers, we need to delete some values. So now the question is how, now it comes to the question, okay, we have this structure. We will maintain this data structure, right? What is the time complexity of this thing? Can we estimate? Can we say for certain that what is the time complexity? And I will give you first hints because first we need to somehow maintain this structure, right? We will only have a binary search tree, so nothing more than a binary search tree. We will have a dictionary essentially. For each x position, we will know which y position it is, so which skyscraper, but we will only keep positions for the frontier. We won't keep all of the positions. 9, and then this will be 0. This 8, at x position 8 here we have 80. At here we have some position where we have 100, so this is position 6, we have 100. We won't keep position 7 because we have 0 here. It's not a part of our frontier, right? Position here where 35 was, so this is position 5, we have now 180, and position 1 we have 200. So let's say these are only our positions. So these can be sorted in some data structure here, and we can, in logarithmic time of n, find any of these. And we can say, okay, if I ask you from position, let's say I ask you from position 4, right? What is the answer from position 4? Given this information, this is our frontier. You see, it's all of these are in decreasing order, all of these are increasing order.
Yeah, so from position 4, what it will be? What's this, 180? 180.
Because we only have to take a look at the next element that change. We don't need to know this element because this element is overtaken. This is called a domination. A side fact, this is a problem connected to one more problem which is called n-dimensional coordinate-wise domination set. this problem, this data structure is used to solve this problem, but this is already a very complicated problem, and we know how to answer questions right now, very quickly, in all log n time. Because we only have n things here, if we have a binary search tree where we search upon these indices, we can just take the index which is a little bit bigger than this index or equal to this. So if ask is 5, then again it's 180. But if ask is 6, then it's 100 because 5 is not included. Now it's the problem, what is the build time complexity? If I make a skyscraper bigger, sometimes this will change only one value, right, in this map, in this dictionary. But sometimes you will have to delete a whole bunch of other skyscrapers that are smaller than this. So if I would to have a skyscraper here built somewhere in like the 12th place, which has a value of 400, I will have to delete all of these other skyscrapers. So, okay, maybe this build query is O of n. Because now we have to delete n skyscrapers, right? Is it really O of n? Can you bound it somehow mathematically?
Да, ако стам тук 400, това значи, че сите тук ги бришам. И сега ще кажеш, що сега ще кажеш да не ги избришам? Мислям да...
Не, морам да ги избришам, няма да холда invariant-а. Няма да холда.
Well, yeah, actually we can see here that we are bounded by 10 to the 5th, right?
Exactly. So the idea is that we will at most have 10 to the 5 skyscrapers that we will ever delete, right? We can't delete more than what we actually put in, right? Sometimes an operation of build will cost us q times q deletions. But other times will cost us only one deletion. So what we say is that each operation has some cost, which is cost in operations, and this is denoted by ti. So t1, t2, t3, and so forth up to tq. These operations, we will only take a look at the build operations right now. So let's imagine that they're all build operations. So each of these operations will delete some skyscrapers, or maybe add a skyscraper. At most, we will add q skyscrapers, and hence at most we will need to delete at most q skyscrapers. So the sum of over all of ti from 0 to q, so all of the ti is somehow bounded by O of q log q, because there will be at most q operations of deletion, so deletion operations, and each deletion, this is the cost to delete, because we know in a binary search tree we will have a log q cost to delete. So actually we see that one operation can be very, very expensive, but the sum of all of the operations is not that expensive. It's only q log q, which is really cool, right? We cannot remove more skyscrapers than we can add, right? And this is why when we have some kind of these invariant data structures, we always think about amortized complexity. And this is essentially what is amortized complexity all about. It's bounding the complexity of a sequence to some asymptotic function instead of having a complexity instead of bounding the complexity for each individual operation. And all of that in few lines of code. How beautiful is geometry, right?